All right, everyone. Today, we're breaking down a super interesting new paper that goes after a core, almost unquestioned part of nearly every modern transformer, the residual connection. So let's dive right in.
So what's the big idea here? Well, the argument is that the same attention mechanism that's been so good at figuring out the importance of different tokens in a sentence can be flipped on its side and used along a new dimension to figure out the importance of different layers in the network.
Okay, so here's our game plan. We're going to start with the standard way of doing things that's being challenged. Then we'll introduce this new idea, attention residuals. After that, we'll look at the performance claims they're making. And finally, we'll put on our skeptic hats and get into the really tough questions the research community is asking.
First things first, to really get what's new here, we have to take a quick look back at a core piece of tech in pretty much every modern deep neural network.
You know, the standard residual connection, that classic x plus f of x, is basically just a passive information highway. It lets information and gradients flow way more easily through these super deep networks, which is how we get to build these massive, powerful models. It's a simple addition, really, and it's been the backbone of deep learning for years. Okay, so that's the old way. Now let's turn to the new proposal from the researchers at Kimi Linear. They're asking a really fundamental question. What if that information highway wasn't so passive? The whole insight here is that the info from every single previous layer probably isn't equally useful for what the model is trying to do right now. So instead of just blindly adding it all up, this new method proposes a much more active, learned process where the model actually uses attention to decide exactly what information it wants to pull forward.
And this slide right here really gets to the heart of it. It's a huge shift in thinking, right? We're moving from a blunt instrument, just plain old addition, to something way more surgical, a learned selective retrieval. This basically turns a static, hard-coded piece of the architecture into a dynamic thing that the model controls, giving it a ton more flexibility.
Of course, a new architecture is cool and all, but does it actually work? Let's get into the performance claims from the paper. The big headline number is a 1.25x compute advantage. Now, this isn't just about being faster. It's about efficiency. What their scaling law experiments suggest is that if you want to hit a certain level of performance, this new architecture needs about 25% less computational power to get there. And they back this up with charts like these, showing performance on really complex math problems. You don't need to squint at all the numbers here. The key thing to look at is the story these trend lines are telling. They're arguing that their architecture shows a steeper improvement curve, meaning it gets better, faster for the same amount of effort, especially as you scale the models up. But you know how it goes in research. A big claim gets made, and then the rest of the community comes in with the tough but necessary questions to see if it really holds up. It's time for reality check. This first point basically says, cool idea, but where are the receipts? It's a call for rigorous ablation studies. That means we need to see true apples-to-apples comparisons, testing the new and old methods with the exact same number of parameters, the same compute, the same data, to really prove that the new architecture is what's making the difference.
And this next one is all about scientific rigor. You know, how do we know these great results weren't just a one-off lucky shot from a good random starting point? It's standard practice to run these experiments multiple times with different random seeds just to be sure.
And here it is. Maybe the biggest question of all for any new architecture today. Does it scale? Look, getting good results on smaller models is a great first step, for sure. But the real test, the one that really matters, is whether those benefits are still there when you scale up to the massive frontier-level models.
So with the big claims and all the caveats on the table, where does that leave us? Let's kind of zoom out and look at the bigger picture here.
What we're really seeing here is the scientific process playing out in real time. You've got a bold new idea, some promising early results, and now the entire global research community jumps in to do the essential work of testing, critiquing, and trying to replicate it. It's awesome.
So this leaves us with the final critical question. And honestly, it's a fantastic reminder that in this field, progress is always this cycle of a bold new idea followed by intense collaborative scrutiny. The real answer will unfold over the next year or so in all the replications and scale-up experiments to come. It's going to be fascinating to watch. Thanks for digging into this with me.